When my friend Polat Gurkan asked me to give another presentation at the Istanbul Bridge Conference after 4 years from my previous presentation on the collapse of the Morandi Bridge, I thought it would have been a good time to give a sort of updating in the sense that 4 years ago we were presenting and discussing results based on publicly available material just 3 or 4 months after the collapse. Today, after 4 years, we have been able to look in much more detail into the available evidence and also to access a lot of material that at that time was considered confidential because of the court case, which was starting at that time and is still on its way today. So this will be the subject of my presentation. I will, first of all, go briefly through the previous evidence. So the early assessment, as I call it, which means what we had available 4 years ago. Those of you who were present can probably remember what I was presenting, but I will go through it quickly. Otherwise, for those who are not listening to the previous presentation, it would be difficult to follow what I'll be commenting today. So the bridge, first of all, the bridge was built in the 60s. In my previous presentation, I gave a lot of background that I will not discuss today. The structure that collapsed was one of the three main spans, which was made with a number of inclined struts that you see in this picture. Was also made by an antenna which was going up to a significant elevation, a main deck with a 5-sector box section with a depth of 4.5 meters and by 4 transverse link girders that were located at the point where the diagonal strut were working and the cable stays, the 4 cable stays were supporting the structure. At the end of this structure, there were 2 simply supported spans that were located at the 2 sides. The construction was quite standard and traditional for what required the construction of the pier and the antenna. The main deck was then constructed in a sequence of 5.5 meter segments that were temporarily sustained by a number of almost horizontal, of course not completely horizontal, cables that were connecting the deck to the other side of the deck. Post-tensioning of the stays was made, as I was saying, through those almost horizontal tendons. At a certain point, at the end of the construction, there were some temporary cables that were then substituted by permanent cables, and those cables were then combined with a kind of a structure, external structure, which was post-tensioned by additional secondary cables to avoid cracking and to increase the stiffness of the structure. In principle, the cables were injected, but this was already a discussion. And at the end, there were the supported spans that were added using prefabricated beams. As you understand, at the end of the 60s, actually was conceived at the end of the 50s and completed in 67. This was quite an advanced structure with spans of around 200 meters, so quite an unusual length for the time. The final bridge was an interesting piece of engineering. Consider that it was built with all the buildings, the railway, a river, and everything which was not touched under the bridge, and has been working for some 50 years before one of the 3 main spans that you see in these slides collapsed. The designer was Professor Riccardo Morandi, who had patented one of the very early pre-compression system or post-tensioning system, as you wish to call it. It was clear already at that time that the space between the duct and the cables was very small with respect to today, so it was very difficult to inject those cables. There was also a minor use of post-tensioning in the main deck. I'm saying minor because at the end, Morandi was counting essentially on the horizontal compression, which was resulting from the fact that the inclination of the stays, like in all cable stay bridges. In 2 points, the deck was supported. At the central point, the one you see on the right in this slide, through compression strut, and on the other side by cable stays. The cable stays were significant section, approximately 1 by 1.2 meters. There were 464 strands in each one of the stays. 352 were the main one, the one that were located first, and 112 were those that were used only to post-tension the concrete. Each one of these stays at the end, in the final stage, was somehow sustaining something in the range of 22, 23 meganewton. The fact that there was some suspicion about the presence or not of injection probably could have been having some effect in the sense of making the structure more sensitive to corrosion, but certainly not any direct effect on potential failure. The supporting spans were made with prefabricated beams, as I was already introducing. Today, they could be considered quite standard, but anyway, significant beams because we were 36 meters long. At that time, at the time of 4 years ago, I was also introducing the fact that during the life of the structure, there has been some early worries about the presence of cracking and other things. And in the 1990, in the early 90s, between 1990 and 1993, one of the main pier was essentially refurbished with new stays located externally with respect to the original stays. It is possible to read in the documents of the time that, according to the designer of the strengthening intervention, there should not have been any problem until something like 2030, something that today probably nobody will dare to sustain something like that. From monitoring, it became clear that there was some absence of injection, there was some corrosion, but the corrosion was limited in the range of 10 to 30%, and so on and so forth. With this information, we went through a number of analyses, using different computer software. For example, using SAP 2000 for preliminary elastic analysis, confirming the fact that the structure had plenty of strength capacity, that would not have been inducing any worries in his original or as designed configuration. But it became also clear that the structure would have never been able to sustain the removal or the collapse on one of the stays that had to be considered somehow a critical element in the structure. We went through seismic analysis because Genova is not a high seismicity, but a medium seismicity region. Essentially, no problem arose. There were some worries for some secondary elements, some horizontal link, and so on, but nothing very serious. We went through detailed analysis of all the capacity of the different sections using, again, different softwares. And it became clear that there were no problems of bending and shear, but there could have been problems related to torsion in case of removal of one of the stays. And this was made clear by plots like this one that you see here, where the green line is showing the demand and the gray figure is giving you the capacity. The final analysis at the time was made through a very complex model. A very complex model used the applied element method. The model was including a large number of degree of freedom. exceeding 500,000 degrees of freedom, representing everything. The results from the point of view of the initial deformation, vertical reaction, axial forces in the stay were essentially consistent with the previous results. But of course, with this method, we were able to go into some really deep and extended nonlinear analysis, showing that even that the progressive deterioration of the reinforcement, corrosion essentially, would have been causing problems only for large level of strength loss in the range of 50 to 70%. And we also went through some analysis to see, in case of some not proven, not evident, falling or anyway impulsive loads, what would have happened. And we examined an impulsive load on the loaded pier on the simple span, examining the case of a point load on a single beam, or examining a complete grid of beams like this one and see what happens for an impulsive load, and also examining the case of a complete span with also the additional slab, and seeing that with the additional slab, the load that was able to induce some failure was in the range of 3,500 kilonewton. Now, the final analysis was showing that even in case of losing a supporting span, nothing would have been happened, and we ended up individuating as a possible initial phase, not cause, initial phase of collapse could have been the loss of capacity of one of the stays, and we were showing that in this case the progression of the collapse might have been compatible with the little evidence that we had at the time, and we were able to show what might have been happening. But the initial event was the removal of one section in the stay. And in this case, what was happening was that also the location of the debris on the ground was essentially compatible with what was evident on the ground. So this was essentially the end of the analysis of the time. We were showing what could have been the initial event of the collapse, and that possibly some exceptional point load might have been the starting case, but nothing more than that. Now, this is, as you see, concluding remarks. What might have happened? What is the evidence that we can add today? First of all, the collapse sequence. Approximately 1 year after the collapse, the court made available one video that was taken by a camera that was located nearby the bridge, and it became evident from this video that actually the starting of the collapse was a failure at the top part of the southeast stay. So this was the first evidence that was completely compatible with what we had discussed. Second thing, it was possible to go through some analysis to try to clarify the differences in the construction sequence. And there were significant geometrical differences. You can see on the left of this slide the as design and as built configuration of one of the pier, which is somehow twisted. But you can see also that the sequence of construction was smart from a certain point of view, in the sense that the concrete added to the stays was added in separate segments, so that the catenary configuration was taken first by the stay, and then it was completed. And going through the prediction by the designer and our modern prediction, which much more powerful tools, it came out that the prediction of the designer was quite good. On the other side, what became also evident is that while the designer had foreseen to have the added supported spans added at the end of the process, so with the concrete stays already working as concrete stays, what happened for Pier 9 was that they added the supported spans much earlier. This makes a lot of difference, but actually it is favorable in the sense that, as you can immediately understand, this means that the supported spans are acting on the primary cables and are not acting on the concrete. On the concrete, on the added concrete, you only have the additional loading coming after this point. So essentially, what happened is that the situation of in the concrete was more favorable. Time-dependent effects, something that in the 60s was not easy to simulate. We were able to show that the state of stress in the cables, in the stays, changed a lot during the life of the structure. Initially, of course, there was a complete compression, like in the upper left plot. You see red is compression, full compression. And then, due to both the combination of creep, shrinkage, additional weights because of new axle, because of additional barriers, and so on, you see that the situation changed completely. Until the 90s, there was an increase, or let's say a decrease of the compression in the upper part, so that temperature or wind or whatever could have been inducing some crack opening, then closed again by compression in the upper part. But then in more recent years, the parts that were subjected to less compression or to tension were the lower part. I'll discuss briefly what this could have as effects on the situation. Not much anyway for what concerns the collapse. Deterioration, here we enter in something which is much more relevant, and this was the situation of the corrosion in the primary and secondary cables in the upper part of the southeast stay, which was detected by some technician that was looking at this. And you see that the level of corrosion up there was in the range of 50–70%, which was what we were assuming to be able to induce a situation which was close to collapse. This is very peculiar because this was only in that part of the stay. In the other remaining part of the stay, the corrosion level of corrosion was much, much less. So we still have to understand why up there so much corrosion, but certainly it gives us a good reason why the collapse started in that region. And I'll discuss this further with some more evidence that I will show you. But in this plot, you see with the blue contour what should have been the moment axial force capacity curve of the stay, and on the right side in red and green you see what the capacity looks like, including corrosion. You can see a rotation. You can see the green line here and here. The green line is because, as I will discuss briefly in a minute, there was also some geometrical differences in the location of the cable. So you have a change because of the geometry and the change because of corrosion. But as you can see here, the change because of corrosion and capacity is much, much more relevant than the change due to geometrical differences. And you can see here other plots. Of course, you can have also out-of-plane bending due to wind, for example. And the plot that you see on the left here is a section in the complete, solid diagram of the capacity of the structure, is a section with a certain level of transversal bending moment. And you see that the permanent loads were still not so close to the capacity. If you include what was the traffic load at the time of collapse, you get closer. If you imagine a potential impact of something that I will discuss later, you could go to the capacity. And you can see on the right another section in the solid volume of the capacity. And this is a moment section with a certain level of axial force. And you can see that with a variation of the bending moments, you can get close to the capacity. Now, differences between as design and as built. You see, this is a picture of the top of the antenna. This is a drawing of the primary cables in red, the secondary cables in blue, the ordinary reinforcement in green. And now it was possible to cut through the remaining part of the structure and see that the situation was quite different. You see one of the section here in the low figure, and you see that the position of the red primary cables and the position, particularly the red primary cable, is somehow all towards one direction of the entire section. But you also see, and I will show it you better in the next slide, that there is some presence of void up here. This was particularly true in the upper 2 meters where there were voids, and there was the sheets was completely missing. And I will show it to you better in this slide, which is again the upper part. You see that this part here is where the vertical element was, and this was the starting of the stay. And you can say that here in this, say 1.52 meters, there were no sheets. So this means that here the cables were directly in contact with the concrete. But also you can see, okay, again here a difference in geometry, but you can see here also the presence of big voids here. You can see absence of cable ducts, and here presence of large voids. This may have favored the progression of corrosion that I was discussing earlier. And you can see a difference in geometry. Now, causes and sequence of collapse. Well, this is the video I was telling you about in one of the first slides. And you can see here the entire video, and you can see the beginning of course, the entire video is just a few seconds, but you can see, I'll show you again this video, and you can see that the beginning of the collapse was in the southeast day up here. You see here is where the failure will start, and then this part here will rotate in this direction. You see, this was very properly reproduced by our model. Now the sequence is now clear. No doubt about the sequence explained by mechanical model. This was a good satisfactory evidence for us. And in what we were also made evident is that in case that there could have been a certain, say, impulsive load in this area here or in this area here, this might have been one of the several possible causes that would be inducing a failure here, which was the weakest part of the structure. Why on August 14, 2018? Well, one possibility, not proven, so I'm not saying that this happened, but there was a truck with a coil passing on the bridge on that day. The coil was not properly connected to the truck. And you can see here, this is the coil in the left, on the right lower figure. You can see the coil here and the truck. So the position could be compatible with the collapse. We tried to model the collapse, I was saying repeatedly, and we were also looking what happened in the past, and we found hundreds of reported coil collapse in the literature. So no evidence that it happened, but no evidence that it did not happen. And anyway, complete compatibility with the collapse of the bridge. Of course, the point here is the red one here. So that the coil fall could have been at the origin of the collapse, but also the location of everything on the ground was compatible with that. Of course, on that day, there was a big storm. There was an abrupt change of temperature. There was a strong wind, very strong wind. So it could well have been that the coil did not collapse, did not fall into the ground, and that other causes were at the origin of the fact that the bridge collapsed that day at that time. Certainly not the traffic, because the traffic was light. Now, one of the crucial questions: could have been the situation assessed and the collapse predicted? Now consider that those two specific situations, the absence of the sheath and the presence of voids that might have been inducing a significant corrosion locally, were extremely difficult to be detected. The section was 1.22 by 0.98 meter, and the voids were well inside at in the center, essentially, so at least 30 or 40 centimeters. Very difficult to be detected unless drilling holes exactly there. I'm not an expert in RINT or any other tests to detect corrosion, so I will not talk about that. But apparently, from those tests, nothing evident came out, inducing to imagine that the corrosion was that advanced. But there is one aspect that I would like to discuss briefly with you, and that is the fact that there have been recently 2 series of dynamic identification, and someone was pretending to affirm that through dynamic identification might have been possible to make evident this situation. Now, this is not true. First of all, because a modification of post-tensioning is not influencing anyhow the mode and the frequencies of vibration of the stays. This comes from many theoretical studies, because there are 2 effects that I have no time to discuss that are compensating each other. But there are other things that were somehow neglected during the dynamic identification that had much effect, a significant effect on the results. And one of these effects was that the length of the bifurcated part was very different in Pier 9 and in Pier 10, with 4 meters differences in the length. Now, if you consider this and you go and you consider the mode and frequencies of vibration, you find that everything is very compatible. Actually, what we did was also to locate a local defect on the top upper part of the southeast stays to see whether it would have been possible to individuate the effect, and the answer is totally impossible. A weak situation there was not influencing the modes and frequencies that were detected. Maybe with having, I don't know, 100 instruments instead of the very few instruments that were located, this might have been possible. I'm not discussing this, but certainly not with the kind of dynamic identification that was performed. Now, conclusive remarks. I think that we should look to the future, and we are not here in a court case, so I'm not discuss in conclusive remarks what are the responsibilities and so on and so forth. But there are 2 points that I would like to raise. One, related to new structures. I think that in general, we are putting too much emphasis on protection factors and not enough emphasis on controlling the quality of constructions, the quality of materials, the presence of significant problems during construction and at the end of the construction phase. Structures are showing us that they do not collapse because you put a protection factor equal to 1.25 instead of 1.3, but because of major problems. And these major problems are often due to big mistakes in design or big mistakes in construction. Unfortunately, only dramatic events are finding out these problems, and nature is very good in finding out problems, not only earthquakes, but all sorts of natural or human-controlled events. This is true for new structures, but for existing structures, which is much more a problem of ours today, I would say that we, again, are putting too much emphasis on doing a large number of tests instead of trying to understand what are the potential critical issues in structure, and then to just use the available resources to try to go in much more depth in what could be a problem for structure. I'm not talking about the Morandi Bridge now. I'm talking about all the numerous cases in which I see a lot of tests and so on without any specific purpose. I think we have to again go back to first understanding structures and then use testing in a continuous interaction with analysis to go in depth where it is useful to go in depth. I thank you all for having listened to me, and I hope this presentation has been of interest. Best regards, and see you next time.